Okay, this is, I don't know what number video for Module 7, talking about the raster model and analysis you can do with raster datasets. I've talked about local and neighborhood and zonal and global operations you can do. Today I'm going to talk about things you can do specifically with terrain, and terrain is based upon an elevation dataset. So way back in Module 2 when we talked about geoids and using a model to model the elevation above mean sea level. When you get a data set, a raster data set, that has cells that give you the value of the elevation above sea level, you can do a bunch of analysis. So that's what the next couple videos are going to be about. Before I start, I need to start talking about this guy right here. When I teach this class live in front of a classroom, I ask people who this is. Very few people know who that is, if any. But this person's name is Waldo Tobler. Okay, big deal. What does he have to do with anything? Well, Waldo Tobler came up with what's called Tobler's first law of geography. So this isn't Robichon's first law of geography, this is Tobler's first law of geography. And Tobler's first law says everything is related to everything else, but near things are more related to each other. So this turns out to be really important when you start doing things like interpolation and terrain analysis. And it's a basic geographic concept. Everything's related to everything else, but things that are close to each other are more related to each other. Think of it as birds of a feather flock together. Okay, that said, let's move into some terrain analysis. There's a bunch of things you can do in what's called the surface tool set of the ARC toolbox. In this video I'm going to talk about slope, aspect, and curvature. Those are all going to use the elevation raster as the input raster. Hillshade also. Okay, what's slope? This is a raster that shows an example of slope. Slope is the steepness of the terrain. So what slope does is it goes out to your elevation raster and it calculates the steepness of the terrain based upon the cells that are surrounding the cell that you're calculating the slope for. So it's a neighborhood operation. There's more than one way to calculate slope. They write papers about which way is best and why. We're going to use the way that ArcGIS used, which is called the Horn's method. And what it does, just like you remember from your days in geometry, the slope is the angle whose tangent is the rise over the run. Okay, we've got rise over run in the x direction and the y direction with our raster data sets. So this is how we're going to calculate that. We're going to take the square root of the sum of the squares of the change of elevation in the x plus the change of the elevation in the y squared. Okay, so here's an example that shows you a neighborhood around this cell. We're going to calculate the slope of this cell. You can see that dx, dz, dx, the change of z with x, would be equivalent to c minus a plus I minus g. Here we have plus 2f minus 2d. Notice the 2's in here. So up here and down here are getting weights of 1, but this row is getting weights of 2. Similarly in the y, you see that the middle row gets weights of 2 and the outside rows get weights of 1. This is all based upon Tobler, right? Things that are closer are more related. So this cell is closer to the center cell than this cell is, because this one's on the diagonal, right? So the distance here is further than the distance here. So when you're calculating slope in this direction, you have to give more weight to the closer cells. So that's what this takes into account. It gives more weight to the closer cells. So that's why we had to talk about Tobler. Okay, moving on. Here's an example. Just looking at this, you see high numbers here, medium numbers here, low numbers here. You can kind of tell that there's some slope in this elevation raster. Let's calculate it. Here's dz dx, so we take c, which is this, minus a, which is this, 50 minus 50, and so on. These two get double the weight, 30s, and that's how you get this answer. Same in the y. You can look at those later and verify that those are the proper calculations. So dz dx, dz dy. We square those two, add them up, and take the square root. We get this number. We calculate the angle whose tangent is that. This thing is going to convert it into degrees, and we see that the slope is 75 degrees, pretty steep slope. So that's what it's doing. It's going through, in a focal neighborhood operation, going through the raster and calculating the slope for every cell. What the heck is the aspect? The aspect is the direction that the slope points. And the way we report aspect geographically is using north as 0 and going clockwise around the compass to 360. Okay, what's aspect going to be? Well, it's going to be an algorithm. And again, we have the angle whose tangent is dz dy over minus dz dx. And so you're going to still use dz dx, dz dy, you do the same kind of calculations, but when you're done you have to convert from angles that start horizontally at 0 to angles that start vertically at north and go in different directions. So this takes care of the conversion from mathematical directions, angular directions, to compass directions. Okay? Again, Tobler's first law, 2, 2, 2, 2. Closer cells get more weight. Here's an example of aspect, and what do we look at here? We see high elevation, medium elevation, low elevation. So it seems like it's sloping from high to low, from west to east, and maybe a little bit south of due east. And so if we do this example and it comes out that the aspect is somewhere around 90 degrees, so 90 degrees clockwise from vertical, then we will have calculated it properly. Plug and chug, dz dx, dz dy. The aspect is minus 2.64. That is the mathematical number. We're going to have to convert that to compass. We convert it to compass, we get 92.64 degrees. And so there's your aspect. It goes through the elevation raster neighborhood operation focal, calculates aspect for every cell. Okay, so what's the curvature? We have the slope is the first derivative of the elevation. The curvature is the second derivative of the elevation, which is the slope of the slope. So it's the rate of change of slope. You should probably remember this from back in the days when you did algebra and things like that. There are different types of slope. There's a profile, which is, you can think of it as taking a slice, a vertical slice out of the terrain. There's a plan, that's like looking down on the terrain. You'll get different curvatures depending upon the direction you look at it from, and you can imagine how you might get different curvatures. If you were taking a vertical slice here, you'd see an inverted U, and if you were taking a horizontal or a plan slice, you might get a different curvature there. There's a combination of plan and profile that's called the standard curvature. Okay, so it's the second derivative of the elevation, it's the slope of the slope. Here we have profile curvatures. So you're taking a vertical slice, and you can see that a negative curvature is convex, so it's curving up. A positive curvature is concave, so you can imagine if this were a hillside, you probably would have negative curvature up high, and then you'd have positive curvature down low, so that makes sense. This would give me the plan curvature looking down on the top, and you can see here that a negative plan curvature is going to be something that's kind of a concave curvature, and a positive is going to be convex. We can combine those two into a standard curvature, and we get this here, and this is generally what gets reported as the curvature. Okay? Again, there's a profile, a plan, and a standard. And when you look at this graphic, you can see or imagine how curvature would be important, especially in hydrological situations of terrain. So you can see where stream channels converge, where stream channels diverge. So it'd be really important in things like erosion and mudslides and things like that, where the water's going to flow over the terrain. Hillshade. Hillshade is an algorithm that goes out to your elevation raster and calculates what you may or may not see from a certain illumination angle. And it shades the output raster, it shades the cells so that the cells that you probably can't see as well are going to be darker than the cells that are illuminated by your source illumination. Okay, that's what hillshade is. So how does hillshade work? You tell it what the azimuth, again azimuth goes from due north clockwise, the azimuth of your illumination or your sun, and the altitude. So here we have azimuth. In this case, the azimuth is out here. This would be 270, this would be 360, so this would be halfway in between those two. And the elevation of the sun, at this case, would probably be, I don't know what that is, 40 degrees. So if you move the sun up, you're going to get brighter cells because more are going to be illuminated. You move it down, a lot more of them will be shaded. And when you move it around the compass, different aspects of the terrain are illuminated. So it's a good way to visualize terrain. The raster itself looks like this with just values for each cell, just like all rasters do. Here's an example of Mount St. Helens before the 1980 eruption. So this uses the elevation raster, which remember is called the Digital Elevation Model, the DEM, of the terrain before 1980. So this is what Mount St. Helens looked like before it blew, and here's what it looks like after it blew. So these are visualizations that use hillshade, and they plot the values of the elevation, and they shade the values of the elevation using the result of hillshade. ArcScene is the application you can use in ArcGIS to do this 3D stuff. And so this is the illustration of what that post-eruption Mount St. Helens looks like using ArcScene. Okay, so that was slope, aspect, curvature, and hillshade. There's a couple more terrain things that we need to look at. We need to look at something called viewshed, and we need to look at something called tin, and then of course making what are called contours from terrain information. So that's what will be in the next video.